Today's speaker in our famous seminar is our own Dr. Michael Kiessling, who will talk about some kind of paradoxes. As usual, please mute yourself unless you have something to say. Thank you.
Good. So that's the title of my talk. Some surprises. Well, at least one surprise I managed to get all finished here for the slides. But you see in the title header, no? So not in the title, but in the summary of the sections, there's Lennard-Jones crystals and Lennard-Jones clusters. So I will be talking basically crystals, and but now we go here. There we go. So I start with the first page. So Lennard-Jones crystals 101. But why 101? So it's not the introductory lecture, but I'm quoting now from a paper. The paper is stated below, and I will show it in a moment. So the first sentence in the introduction starts with on April 22, 1924. That means it's 101 years ago, up to a few days. The Royal Society of London received a paper written by a research student at Trinity College at Cambridge, John Edward Jones, and so on and so on. And somewhat later in the article, not far later, still in the introduction, you read, in Lennard-Jones's third paper of 1924, so still 101 years ago, lattice sums were introduced to obtain bulk properties for cubic crystals. This work is particularly interesting and perhaps less well known to the chemistry community, as it opened up a whole new field in mathematical lattice theory. Okay, so, and I said I quoted this from this paper by Peter Schwertfeger and David Wales. And the title is 100 Years of the Lennard-Jones Potential, while 100 years, well, it was published in 2024. So let me stop sharing and show you now exactly this other paper. So where did it go? My goodness. So again, now I click. No. I see my paper now. So let's. How do I switch now, Dimitri? I cannot believe this. Now I have the opposite problem.
Is it opened, the file?
Yeah, I opened it. But if I click share,
to share again, yeah.
Then it will pop up possibly now my.
Yeah.
No, there it is. Ha, very good.
Not...
Enter full screen. So you can see this paper, 100 Years of Lennard-Jones Potential.
Can you zoom in a little bit?
Yes, but make it bigger, please. Yeah,
Like,
that's better. That's good.
Good enough. Good. All right. So here's the man. And but 100 years ago, he was not Lennard-Jones. He was just Jones. And so that was when he was a PhD student at Cambridge. And the reason it's Lennard-Jones is, well, it's difficult to keep up with the Joneses if your name is Jones in particular. So he married a woman whose name was Leonard. And so he added the family name of his wife to his name.
Oh, so it's only one person. It's not a collaboration of two people.
Exactly. No, many people think it's a collaboration of two people. No, he added the family name of his then-to-be wife after marriage to his name and became Lennard-Jones ever since. No? And so this is a photo of the man. And so you see already here some potential that it will be talked about. I will use a slightly different notation, but the index here is LJ for Lennard-Jones. And so R is some distance between atoms, and N and M are natural numbers, usually powers, and then you have some coefficients. So that's what he talked about in this paper. And so in any case, so here you see already upper right corner, there's also a cluster. That's not anything that he did back then. That's impossible at the time. This is computer generated. And so in any case, I really can recommend this paper. It's not very long. It's some celebratory paper about this 100-year event, and it has more than 450 interesting references. Now, it's written by two theoretical chemists, and that's just an advertisement here for this paper. And let's go back now to stop share here, and I want to get back to my slides. Hopefully they will now pop up. Keep fingers crossed. I have that same problem as before. It's curious that
I guess you should indeed wait a bit more.
I
You should
think
be patient. It takes
yeah,
time to load.
yeah, okay, maybe that's the point, yeah. And so okay, give it another shot here. Click, wait a little bit, wait and wait and wait. Now I share. There we go. Yeah, thanks for the hint to wait a little bit.
Yeah, looks good.
Looks good. So now let's go on. And no? How do I move on now here?
Try with the arrows on the keyboard. Or...
Maybe here's something that I don't want here. There we go. Now I had to close some application that popped up. Okay, so here you see now the same potential that I showed in the paper on page 1. I use the modern notation of V here. And so once again, this is the R is the distance between two atoms. And it's positive, of course, and measured center to center. N and M are positive, and N is bigger than M, obviously, because you want stability for short distances, and at the same time, for long distance, you want that the attractive part overwhelms the repulsive part so that you get bonding, right? And so good. So this is the general family of Lennard-Jones potentials here, as chemists usually call it. There's an interesting aspect you read also in this paper by Schwertfeger and David Wales, namely that this potential was actually exactly the whole family with all the same assumptions proposed in 1912 by Eduard Grüneisen. And he himself was inspired by a paper almost 10 years earlier written by Gustav Mie from 1903. Gustav Mie also proposed this family, but it shows n equals 5. And so then Grüneisen said, oh, let's look at more general n and corresponding m's. And but these were solid state physicists. And in the chemistry community where Lennard-Jones grew up, so people don't necessarily look into what the solid state people do. But so anyway, in the solid state community, this thing is often called the Grüneisen potential for that reason. Okay, good. So now here, next title, the Lennard-Jones potential, and that's the famous 12-6 potential. And this became a kind of a standard for the main reason that this power 6 for little m, yeah, you can derive this from either quantum mechanics, but also from Newtonian mechanics. If you, let's say, I say updated Newtonian mechanics, I teach that to my students usually, that you take electric Coulomb interactions, and but you also introduce some stabilizing short-range interactions. Newton was thinking of billiard balls. Okay, make it point particles, but with a inverse power, for instance. And and assume you have two types of particles, nuclei that are positive, and you have electrons that are negatively charged. And so then you can actually compute that if you have two neutral atoms with lots of electrons around them, but they are far apart, that there is an induced dipole moment, right? And so the dipole-dipole interaction, the attractive part, that goes like 1 over the cubic distance, but the strength of the coupling constant is also proportional to the cubic 1 over cubic distance. So if you put it both together, you get 1 over distance to the power 6. And quantum mechanics yields that same result. So this part here is quite reasonable to assume. And the power 12 is simply for convenience. You need something that decays much faster. So why not double the 6? Because then you can use a quadratic formula for many computations. So this here is not something to be derived from quantum physics. It's just for convenience. The funny thing is that with two constants, epsilon and sigma here, that are matched to the type of atoms you have, This is a very successful, effective potential using Newtonian physics to describe, for instance, the noble gases. Not helium. Helium is too light, but argon, neon, xenon, radon, right? So when you look at the computations that people do theoretically with the help of this potential, pair potential energy, and compare that to measurements in the lab, it's remarkably accurate. Now, with only 2 parameters to fit, and you get a lot of mileage out of that. So, okay.
But I don't understand. This is just made up, so you get nice analysis.
That's right. The point is that this here can be justified. This here is just for stabilizing reasons. No? And Y12, as I said, that's just twice the 6. So you have some quadratic and linear term in 1 over r to the 6. And so that's for convenience. So that doesn't change much. But what is important is you match sigma and epsilon to a particular type of atom, right?
But in real life, it is 0?
No. And you have something else here. Quantum mechanics stabilizes instead of this.
Yeah? So it's an approximation to the real world, right?
That's right. That's a Newtonian, basically, substitution for quantum mechanics, so to speak.
Thank you.
But the interesting thing is that what I learned from chemists is that it's extremely accurate. You don't get the correct physics of individual atoms, etc. But once you assume things like hydrogen trimer exists, right? So you have 2 hydrogen, 1 oxygen atom, they bond to a 3-atom molecule, and then you take those as building blocks. So this is part of the interaction that people write down, and they add some Coulomb terms because of polarization there. And they get a lot of mileage out of that, even at the cluster size of atomic clusters. I was surprised because normally you think that, oh, you have to use quantum mechanics. No, the chemists don't do quantum mechanics for that. They use Newtonian physics. So this is effective only, but extremely successful. So for our theoretical consideration, of course, I make life easier. I choose sigma 1 and I choose epsilon to be 1/4. So this is also 1 in the front here. Good. Okay, 1 year later, 101 plus 1 is, no, minus 1, it's 100 years ago in 25. At that time, that was still Mr. Jones, but he was joined now by Albert Ingham, a mathematician who had studied lattice sums. And because Jones was interested in crystals also, so they teamed up and they published this paper on the calculation of certain crystal potential constants and on the cubic crystal of least potential energy. All right, so I put that in bold because that is something I want to talk about a little longer. And so they concluded that among the standard cubic lattices, namely face-centered cubic, body-centered cubic, or simple cubic, that's the 3 types of lattice that they looked at, so that the FCC lattice has the lowest energy per particle. So why energy per particle? Well, the total energy will go to minus infinite if you add up all the pair energies. So this is, of course, a supposedly infinite crystal arrangement of these atoms, and represented by points with Lennard-Jones interactions. And so what people do is they take something that is called a thermodynamic limit. That means you take a finite subset of it, and then you make that subset grow uniformly in space, make it bigger and bigger. So the number of atoms in your subset grows with n. So you divide by n and you look at the energy per particle. That's the relevant quantity that you are interested in. And then they computed this and found that by comparing these 3 structures, that FCC has the lowest energy per particle. And it was almost 100 years later until it was shown that there is something better. Namely, if you take the hexagonal closed packing, that
they were only comparing 3 things, right? It's not a very powerful optimality.
No, of course, they do what they could do, right? And then much later, of course, people had powerful computers. And for a while, one was actually convinced, apparently, when you read the literature at least, that FCC actually does the trick, okay, when n is large enough. No? And of course, you cannot really simulate infinitely big systems. But so it was Betermin and Shammai, inspired actually by more accurate and more powerful numerical simulation that were done a few years earlier. I forgot to dig out which team was doing that. So these are now, Shammai is a physicist, Betermin a mathematician, so they teamed up, and they actually proved that indeed the HCP packing has a lower energy per particle than FCC in the thermodynamic limit. No? So, questions on non-lattice, I mean irregular packing, so they are not addressed here, whether that can possibly beat it, some classy structure. So in any event, so this paper by Jones and Ingham that has become a kind of template for computing crystal structures, and often they do match those seen in nature. Of course, nature doesn't provide you with infinite crystals, but so you make an idealization of an infinite crystal, and then you just take a chunk of it and compare it to what you see in the lab, and that often comes out quite close to reality. So let me give you a toy model to how this goes.
Michael, did they imply that the HCP is optimal over all arrangements, lattice or non-lattice?
No.
How many did they compare?
No, I think they really compared it only with the FCC. That FCC had been done, as I said earlier, compared to BCC and simple cubic. This is not a result that is telling you that this is now the best result among also non-lattice packings. There's no rigorous result, as far as I know, available. The point is people are happy because of numerical simulations where you don't assume you are necessarily on a lattice. You run minimization algorithms, but there, of course, is all NP hard. No? So this is everything has to be taken with a grain of salt in these simulations, whether you can, how much you can trust them. No? But
yes, okay.
People do that again and again, and then there's a consensus that forms. And well, until maybe somebody finds something better. No? But then among those four lattice structures, HCP is the best in the thermodynamic limit. But let's go to this toy model. I call it the one-dimensional illustration. So suppose you arrange infinitely many of these Lennard-Jones atoms, which simply, once again, means point particles with a Lennard-Jones pair interaction, and you place them on a lattice A times the integers. No? And A positive is the spacing between any two consecutive lattice points here. Okay, doc. Then the potential Lennard-Jones energy per particle, I write it as W of A here, is identical to the potential energy of any particular point particle that you choose. No? Pick one you like. And then you ask for what is its potential energy in this infinite chain of point particles. That means you simply sum all the pair energies of the Lennard-Jones type. And the pair distances, of course, they are absolute Ka, right, where K is running over all integers except 0, of course, because the particles don't interact with themselves in this assumption. So they only interact pairwise. Okay, you do that. Well, the powers are high enough, right? So these sums here, they converge when C is bigger than 1, and our C's are either 6 or 12, so we are good. So, and you can just work that out, and you see by scaling the A comes out, you get an A to the 12, 1 over A to the 12 in the first sum, that's the repulsive term, and then 1 over A to the 6 in the second sum, and the rest is just a Dirichlet series of the zeta function over some particular real values. So you get the factor 2 is because you're summing over the integers except 0, so it's like twice summing over the natural numbers. So 2 times the zeta function of 12 divided by A to the 12 minus 2 times the zeta function of 6 divided by A to the 6. And here it is. That's how this beast looks. So down here, here's 0, that is the A-axis, and here's now the total potential energy per particle of the whole chain, or just, which is the same thing as the total potential energy of any particular particle in the chain as a function of the lattice spacing. So you see there is a unique minimum here. So this is the 1 over A to the 12 part. This is the negative 1 over A to the 6 part. That of course, dominates for large distances, but this is easy to compute. And here it is. So there's a unique lattice spacing A sub min, which gives you the lowest potential energy here. And so, by the way, that interestingly is the whole expression is proportional to pi, because zeta of 12 is proportional to pi to the 12. Zeta of 6 is pi to the 6. So you divide it, you get pi to the 6 in the ratio, and there's the 1/6 root. So the whole thing is proportional to pi here. Anyway, so in red, choosing A to be A min gives you the infinitely long idealization.
It is 1.19 blah 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 times pi.
Yeah. I computed that also, but I didn't put it in the slides. That's right. It's close to 1. And so this gives you now, in this toy model, the infinitely long idealization of a Lennard-Jones crystal in a hypothetical one-dimensional world. By world, I mean space. No? So, of course, time is to be added. Okay. So, but why minimizing energy gives the right physics? Well, it usually comes out quite right by doing that. Well, the usual narrative is that without kinetic energy in the system, and notice I didn't talk about temperature, right? So I'm neglecting the influence of temperature, which would cause these atoms to jiggle around their equilibrium lattice positions. So the stable crystal state is attained when each atom is in its lowest energy state. That means minimizing with respect to A gives you just that. So that's the narrative. But why that narrative? Okay, answer. Well, it comes, of course, all as extractions from empirical observations. Just think of what happens to the familiar water, right? So if you slowly cool down a liquid like liquid water, it will eventually crystallize into solid water ice, having lower energy than the same amount of liquid water at higher temperature. Our physical theories, they are just designed to reflect those observations in the mathematics of our idealized models of nature. And so it's tried and found to work, right? So, okay, good. All right. Let's, I just mentioned temperature will make things jiggle. So now we asked about small oscillations about the stable equilibrium, right? So, okay. Let's compute Newton's equation of motion for each atom. Good. So if two particles, no, so pick any two at locations, now we are still on the line, of course, I'm just sticking with my toy model here. So two particles are at the locations X and Y. And they have a Lennard-Jones pair interaction energy that I had defined before, but now, of course, R is simply the absolute value of the Euclidean distance in 1D between X and Y. No? So X minus Y absolutely. So then the Newtonian force, that's what you learn in high school, of particle at Y on the particle at X is the negative X gradient of the Lennard-Jones potential written in this form, okay? And it obeys Newton's principle that actio equals reactio, meaning that the force on particle at X from the particle at Y is the negative of the force on the particle at Y from the particle at X. Okay, so that's this formula. And Newton's equation of motion is then for all I in the integers, the second time derivative of the position as a function of time of the ith particle is given by the sum over all the forces exerted by all the other particles. So J is not I, you sum over all J in the integers except J equals I itself. So that's Newton's equation of motion. That's infinitely many equations of motion. Now that's, of course, not such an easy thing to study in general. So let's make things even more simple and look at the simplest problem that can come to mind of the dynamical nature here. I call that dilational dynamics. So the oscillatory motions of perturbed lattices, right? Because they can be so complicated, let's look at the following. Imagine the infinite Lennard-Jones chain to be either compressed or stretched uniformly away from its equilibrium state and then released from such a constrained state. So I've actually prepared an experiment here. I took my pen apart, and you see here some toy model. Can you see this? This is when I hold it like this with my beard in the background, you see there's a little spring. So of course you can picture that as a chain of Lennard-Jones particles, and I can either pull this roughly uniformly, or I compress it away from its equilibrium state that it has, and then release, right? So so everybody can do that with a spring, and then you know what happens. And so good. So this is it, and the keyword here is uniformly. So we cleverly anticipate that the final result of a lengthy calculation with our infinite system of equations of motion will be an effective differential equation for the lattice spacing A as a function of t now. Namely, the second time derivative of A is a negative gradient of just that pair potential as a function of R, but evaluated when R is A of t. Okay, doc, so that looks good. What are the initial data? Well, the initial A is some A sub 0, that should not be the minimum A, and d over dt, the initial velocity, is 0. Why? Because let's say I stretch it, I pull, hold it, and then let go. Or I squeeze it together, I compress it, hold it, and then let go. So that's the idea. So either it boom goes out, or it starts to shrink, and then because I didn't put any dissipation in here, no friction, so that should now keep oscillating. And sure enough, this simple ODE is something that can be solved by what is called the energy method. We actually teach that to our undergraduates, maybe not with such complicated functions in there, but so this energy method yields, actually, let me briefly, for the people that do discrete math and don't think so much about differential equation, what do you do here, right? So this can be simply computed. These are just inverse powers here. You take the derivatives here and then evaluate the results at A of t, okay? Now you multiply the whole thing by the first time derivative of A, okay? So now what do you have on the left side? It's the product of the first time derivative of A times the second time derivative of A. Okay, what is this? This is 1/2 times the first time derivative of the product of the first time derivative with itself. So it's d over dt of A in parentheses squared, and then you take the time derivative of that, no? And then, of course, that will bring down a 2. You don't see a 2 here, so you also have to multiply by 1/2. So that's easy. That's the first time derivative of the square of a first time derivative with a 1/2. At the right side, you have d over dr at A of t times d over dt of A, right? So now if you integrate that over dt, you have a time derivative here that gets killed by the integration. And here you have something d over dr at A times dA over dt, and then you integrate dt. So that kills the dt in well, substitution of variables, and you get an R integral of something that is d over dr. Well, that kills the d over dr, so you get just back that one. No? And so then you just take square roots, and you get an dA over dt is some square root thing. Well, that's too complicated. You just flip it upside down. You get dt over dA is 1 over the square root, and then you integrate over dA, and there we go. That's the answer. So you get a closed form expression in terms of a quadrature. The only problem is that if I would even have a much simpler thing like that, that gives you a sine and cosine, this would be something like an arc sine. So this is not something that is arbitrarily extendable. That's why I said.
So do you have WR? You know what it is?
Yeah. The W of A is this here. Except here you have your R, and here it's an A. That's the initial data A naught. No, and here's your function W of R, and you integrate over the R. No?
So you invert it.
Yeah. And here's A naught again, and A is your running variable now. No? So you have to choose plus minus depending on. That's because you take a square root, could be plus or minus, right? It depends on whether the motion goes inward or outward. And that's already telling you also that in general, when you want to go for arbitrarily long times, you have to always go from one turning point to the other and then flip the sign around, change the initial data, and keep going. So it's a pretty painful process in general, but of course you can do things in principle like that. No? And in the small amplitude approximation, that means if A naught is very near to the minimizing A, then you can linearize the whole thing, and then you get just harmonic motions. And here's then the solution that I wrote down. I didn't bother to compute the omega. The omega depends on the constants of the Lennard-Jones potential. No? So, but that's just a harmonic motion in the neighborhood of the minimizing. So far, so good. But what we did is we took a clever shortcut, right? So let's check whether this ingenious guess, ingenious in quote, is correct. So we evaluate now really the total Newtonian force acting on any particular point particle in this stipulated initial state of the chain of evenly spaced, infinitely many Lennard-Jones atoms with nearest neighbor spacing A, which is not the minimizing A. Okay. Let's be clever again and use the symmetry of the chain. For each natural number k, the particle indexed I feels, in quotes, a particle a distance ka to its right, and another one a distance negative ka to its left, just by the symmetry. Now notice that for each I, you pick an I and choose any k in natural numbers. Yeah, so here's the force on particle xi from a particle that is ka distances to the right, I mean ka steps to the right of particle I. And here is the force on particle x sub I, or particle I, from particle that is negative, in the negative direction, k times a steps away from particle I. And it's easy to see, actually, when you write down not this, whatever, compressed formula, but you write down the explicit expression you get from Lennard-Jones, then this is negative that. But this and this has to be added. So you get 0, and then you go over all of these guys and you get 0. So the total force on each particle initially vanishes. The chain is in equilibrium for any A, because the result doesn't depend on which I you picked, and it didn't depend on A at all. Okay. You seem to have arrived at a paradoxical situation. What is going on? I already put the first bullet point here. No, we tried to be ingenious here. No? So maybe we were too ingenious. But let me challenge the audience. Any idea? So it cannot be both correct, right? So at the same time, something is fishy here. Any suggestions?
So you did two clever things, two ingenious things?
Yeah. Once I came up with some saying, yeah, let's guess what could come out, and I get an equation for the A of t. And then I said, let's really go as Newton said we should do and compute the forces on each particle really, and not some effective equation for an effective spacing A already. But and then I was ingenious again by saying, oh, I'm using symmetry here, right? And so I see pairwise there are lots of zeros, and then I added all the zeros, and I said that's the total force. So
probably you can do either of them, but not both of them. That's my guess.
Yeah, well, they cannot both be right in the same way. That's true, no? But I can tell you one is wrong and one is not wrong.
Thank you. Interesting.
So anyway, so any other suggestions? So, okay, let me go on. So I think that the conclusion that the infinite chain is in equilibrium for any A is really completely counterintuitive. Do you all agree? Yeah. So at least that sounds like, how can it be? How can that be, right? So after all, here's my infinite chain again. And well, a truncated infinite chain, but if I pull it, right, and let go, bong, so this is just snapping back. So that's, how can that be? How can that be? So let's expect our clever symmetry argument that I used. we did a particular partial summation first, namely the left and right step. So we added this for each k, and then we summed over all k. Is this allowed? Well, it turns out yes. And the reason is simply that the series are absolutely summable. So I can resum as I want, I always get the same result. So this is actually the first guess where something may have gone wrong, but it's not gone wrong here. So the upshot is, because of the absolute summability, the infinite chain is in a force equilibrium for any A. It is counterintuitive, but true nevertheless, right? But how can that be? How can that be? Where does our intuition come from? Well, our intuition comes not from infinity. No, I know Doron doesn't like infinity.
Yeah, so it's meaningless. It's not a thing.
No, it's not meaningless. I disagree with that. But the point is, it's to conclude from everything you compute with infinity here, to conclude something about the spring. Yeah, that is the fatal thing. Now, of course, the spring is doing the more reasonable thing you see with the A of t. But the setup with the infinite chain, this is a correct conclusion. This is what the infinite chain gives you when you compute the forces on each particle. So therefore, what's mathematically wrong with the oscillating A of t argument? No? So suppose the infinite chain is oscillating with periodic lattice spacing A of t as computed.
But strictly speaking, you only have a finite chain, and then take the limit
exactly.
and take to infinity if it exists.
Exactly. That one should really do. I started flatly from infinity here, and that's where all the confusion comes from. No? So, but here is actually already you see that it has to be this A of t argument. How would you now actually picture this in one-dimensional physical space, that you have an oscillating chain oscillating with the A of t, you know, that is periodic. So you could fix particle, let's say, pick one I and say this is at the origin, no, the I equals 0, and say x sub I is the origin, fix it there, and then x, that's what this means, x0 of t is 0 for all time. And all other particles with I bigger than 0, they always move in the same direction, either all away from x0 when A dot is positive, or toward x naught when A dot is negative, and all the particles with negative index I, they behave exactly in the opposite way. So it's either going this way or that way. And good. That's how we picture this thing. And that comes relatively close to what a spring would be doing. Now, of course, this doesn't go on forever because friction overwhelms everything here. But the point is, what's so special about I equals 0? Nothing, right? I could have picked any other particle and say, oh, that's not moving, right? And so our visualization actually breaks the symmetry. We break the symmetry arbitrarily. And but by assuming something doesn't move and everything else would move. But in the stipulated initial value problem for the infinite chain with spacing A, the particles of a chain, they would not know which one should stay put and which others not. No? So in fact, they don't move. And also I fooled you guys when I said, oh, here we have this Lennard-Jones force. I can write down any funny force as long as you have this symmetry relationship, even only repulsive forces, right? And you would say, what? I have only repulsive forces from here and only from there. Yeah, but in the infinite chain, they all add up and by symmetry are 0. No? They can also all be attractive and add up to 0. No? So yeah, that's something that is basically the resolution there. And so if there are any questions, maybe before I go on, so let me go back to that picture. It got a little bit cut off here at the bottom, but sorry. So, any questions on this?
So you resolve the paradox?
Yeah, that is basically the resolution here. The point is the conclusion that there is an A of t, that this would be the effective result coming from this Newtonian calculation. That's wrong. At the same time, if one does what you suggested, you actually start with a finite chain, which is, of course, much more complicated, right? And of course, also a finite chain will not be perfectly spaced with all the equal spacings A, right? Because the central particle will definitely feel different forces than the particles at the edges. So there are, it's not just a truncated perfect lattice anymore. So there are, and then the whole thing oscillates, and then you look at what happens to subchains of, let's say, compact support when you take the limit of an infinitely long chain, right? And when you do this, you get your A of t, right? And that is actually what gets much closer to what you see in a lab. But that's a different limiting process. Here I started flatly from the infinite setup, and then basically come to funny conclusions. But they are the correct conclusions, that nothing moves when you start from the infinite setup because of lots of cancellations. And what is tacitly put in to come to conclude there's an A of t, this did not really use the infinite setup, but is what you get by starting from a finite setup and then taking the limit to an infinite chain. Huh? So these two, it just doesn't commute, huh, what you do. That's
neat. Yeah.
So anyway, so when I first hit that, of course, that wasn't clear to me right away that this is then the answer. I was perplexed. And so I ran it by some colleagues from the physics department, and they said, interesting, let me think about it. And so, yeah, this is something that, because people usually, they do what one always does, which is based on positive feedback, it works. And so then you don't try something else. And but if then somebody else does it, like yours truly here, and finds a funny result, then everybody is perplexed. No? So it's because it comes unexpected. Okay, so I just have a few more minutes. So I just get started with something so that there were some surprises that I can tell you, but I didn't really have time to finish my slides, unfortunately. So I will say that in words later. No, but so what about clusters? So remember what I showed you from the paper of Schwertfeger and David Wales. In the upper right corner already, they show you a cluster. When you later go into the paper, there are many more pictures of n-body clusters. And this is a highly interesting problem. It's NP hard. And when n is between 2 and, let's say, 2000. So this is not to be taken too seriously, but 2 is, of course, easy. What's the optimal configuration? Well, just a dime or plop, they stick together. N equals 3 is also easy. You get an equilateral triangular arrangement. N equals 4 is also easy. You get the regular tetrahedron. And these are the easy cases that one can show this is optimizing configuration. Already when n equals 5, it's not easy to figure out what exactly is going on. You can think of the square pyramid with one item on top, one other number on top, or you can take a triangular bipyramid and think about which one is the optimizer. And and then it gets more and more complicated. And so this is an NP-hard problem indeed that has been proven. And but in any case, with a modern powerful computer, so up to n equals 2000, people definitely are optimistic. One can run several necessary criteria for optimality, and these data do pass. Actually, I did that with an undergraduate student, and we found one outlier. It turned out that was a computer-generated typo. Because, of course, there's nobody who types all the energy data into these long lists. It's the computer makes the output. And there was one data point that failed the optimality test. And so we wrote a paper, published this. And that's how David Wales got in contact with me and said, oh, this is so interesting. And then other chemists said, that's so interesting. And then somebody said, oh, I checked the configuration that actually is listed and computed the energy again. I get something that is different at the 5th digit or 5th decimal place, and then it passes your test criterion. So that means the test criterion I had developed is actually quite sensitive. So it picks up things that outliers that are 5 decimal places behind the leading point. And but unfortunately, it turned out to be a computer-generated typo in the data list.
It was a round of error or a real typo?
No, a real typo, a misprint, but it, as I said, it is it's not a human that types in these data. It's a computer computes them and then spits out these long lists. And for some reason, I think the 5th decimal place after the decimal point was wrong. No, it's something like that. So it's even though the configuration that was listed was apparently the best anybody had found.
But that's scary. Maybe somebody copied and pasted it.
Oh yeah, it went by now. It was in various databases, no? So that because everybody copies from the others. So my paper got published in a theoretical chemistry journal, no? Because we're happy to know that there is a misprint in some of the database. But anyway, so we started a collaboration on this with more complicated questions. And so the point is that, see, when n is up to 100, all these you can really have good confidence, but then it becomes less and less certain. And but the interesting part is there are lots of structural transitions, like people say analogs of phase transitions, like between different. Yeah, these are not really crystals, no, because they're too small, no, but there's something called the Mackey icosahedron and the anti-Mackey icosahedron, and then there are decahedral structures. And if you change n, it flip-flops around from here and there, and only when n gets large, it seems to settle for a while in something like an FCC structure. I didn't write that here, and then much later, it seems to go over into HCP indeed, no, and so. Okay, one can expect when n gets really large, then, however, you are in the thermodynamic limit regime, and so there should be something like an asymptotic expansion. And I wrote that the energy as a function of n should be something proportional to the volume of your optimal supercluster, if you want, plus a correction that is proportional to the surface area, plus a correction that is proportional to the edge length, then a correction that is proportional to the number of corners you have, and then, then you run out of geometrical quantities of macroscopic geometry, and then there are atomic contributions. That is expected, no? And this is what you usually get from the thermodynamic limit. These are corrections of an asymptotic expansion, and so one would like to compute that. Of course, here's n, here's V, A, E, C. How does V go? V is proportional to n, A is proportional to n to 2/3, E is proportional to n to 1/3, C is a constant, for instance, 8 corners for the cube, right? And and atomic contributions, these are less regular, so one doesn't expect that this keeps continuing. And we started to look into this for something simpler, namely, for instance, let n and m go, n be 2m, and we let that to infinity, you get sticky hard spheres. In 2D, this was actually solved by Harborn in 1974 completely. This is the optimal number of sticky points you can have. So now you can expand that in n and see what happens. But this is 2D, right? And it's this particular limit. And so that's how far I got. We did a few simple things, and we got some surprises here too. But in the sense that we have some simple cases also in 2D, where you see that the expansion in powers of n to some powers of n doesn't stop. It just keeps going forever. So, which is very different from what one expects here, that there are atomic contributions. That means you get some jiggy-jaggy things happening, no? So we were surprised about that. But this is something maybe for the next talk. Okay, I stop here.
Thank you very much for very dynamical and engaging talk. Any questions to Michael? Well, it's really interesting how you got this collaboration because you found a typo.
Yes. Yeah. Now the point is, of course, that the typo, nobody knew at the beginning there was a typo. People got excited that what there's a non-optimal configuration in our data list. We know that so many people have checked that, and then it turned out to be just a typo. But because the test criterion, it's just a monotonicity, that the average pair energy, right? So that means you take the total energy and divide by the number of pairs, as n choose 2. It's very easy to prove that this has to be monotonic, increasing along a sequence of optimal energy clusters. And so you check for this monotonicity, you know? And if something from n to n plus 1 is not monotonic increasing, then there must be something wrong with the n, no?
So that's how you found it.
That's how it was found. And I have done this on other problems. and I found 2 outliers. No? So in the Thomson problem, for instance, that people had this repulsive points with Reese energy on the spheres. And but anyway, no, David Wales got interested in that criterion and said, can you also do water clusters? I said, oh my God, no, I have just points with pair interactions. Water is so much more complicated. Let me think about it. And it turned out that this was a red herring, that I have to stick to points with pair interaction that depend only on the distance. What is really needed is that you have a pair interaction that is symmetric, but it doesn't need to depend only on the distance. It can depend on the orientation, etc. Like for this triangular arrangements that you get for H2O, right? And then he said, can you do that also for n-body interactions other than 2? For instance, 3-body and so on. And I thought about it, and it turned out, yeah, you can generalize that too. And then he said, can you do that for mixtures of this and that? Yeah, under certain circumstances. So we can do Axelrod-Teller. So that is pair and triple dipole interaction. So, and we wrote a paper that got published in Journal of Statistical Physics. No? And so we continue.
That's nice. Did you find any other errors in the original?
No, not in the Lennard-Jones database anymore, right? Yeah. I also did these water clusters, but because this is much more complicated, the water cluster database has only something like 30 data points. And they
for the original table, everything else was correct except...
Yes, in the original data.
You checked everything.
That was right. And then, but we now, together with an undergraduate student, James Saba here at Rutgers, so David said, oh, we should do Morse clusters with different scaling parameter rho in there. And so James Saba actually went through the lists that are there at the Cambridge Cluster Database and pushed them by a factor 3.5 further. Right, so so that's when the computer also starts getting hiccup, and implemented this test criterion so that you don't just stop after so much searching and say this is the lowest energy found, but you check whether the lowest energy configuration found, whether it passes the monotonicity test, and all those data did pass. But this is only a necessary criterion. It's not sufficient for minimality. It's always possible that there's something else better that you overlook, but it must be very close to the truth, otherwise it would not pass the test. No?
Thank you. Very interesting.
That hasn't been published yet, but we will do that. No?
Thank you. Other questions to David, to Michael, to Professor Kiessling? Well, thanks so much for a very interesting talk. And please email me the slides when you have a chance. And the recording will be available in a few days.
Sure.
Okay. So thanks, everybody. See you next week.
Thanks for listening. Bye.
Bye-bye. Thank you.